Welcome back. So you may remember me from a couple of hours ago. So what I'm going to do in this last session is try to talk a little bit about some of the richer models and some of the complications that come up as we really try to push these models into real-world settings. So there are a number of different things that come up. So I'm going to talk a little bit about scalability. We've talked about, I think Aranesh had some examples of that. The issue of human behavior, robustness to uncertainty, learning, and finally, evaluation. So we left off this morning, and I had talked us through some very basic game models. What is a security game? How do we think about game theoretic reasoning and reasoning about an adversary in this very simple 2x2 kind of scenario? And we all know that the real world is not this simplified. There's way more than two actions. We may not know these numbers in the payoff matrix exactly. There may be unexpected actions that occur outside of these actions that we've modeled. And so these are all the problems that get us excited as researchers, because these are the novel challenges, and they come up as we start tackling new domains. So let me give you one additional story about how this really came about, leading us into the scalability challenge, really for the first major time. So I arrived at USC in late 2008, and they just finished the armor application that I talked about, the airport checkpoint and canine allocation system. And we were just starting a project with the Federal Air Marshal Service to develop this system that eventually became called the IRA System for Intelligent Randomization and Scheduling. So this was designed for the Federal Air Marshal Service. Most of you probably know who the Air Marshals are and what they do. They're basically in-flight law enforcement. They're assigned to commercial airline flights. And like many of the problems that we've talked about, the core problem is that there are not enough air marshals to assign an air marshal or an air marshal team to every flight. The scale of the problem at the time we were looking at least was approximately 30,000 flights per day, 27,000 or so in the domestic sector, and 2,000 or so in the international sector. And even by itself, before we start thinking about the adversarial nature of the problem at all, this would be a massive scheduling problem. Right? It's a very difficult problem just to solve. Just meeting all of the constraints that you have on the schedules. We can't teleport an air marshal from one place to another. We can't put them on two flights at the same time. And there's even some further constraints in terms of duty hours and so forth, all of which have to be captured just to get a feasible schedule that you can actually fly. Then we add on top of that the main concern that we were trying to address here, which is that we don't want to be flying predictable schedules that somebody could figure out that you're always on this flight on Monday morning and never on the afternoon flight from Dallas to Chicago, or whatever it is. So we started doing some preliminary analysis. We looked at even a very simple case where we had 10 officers and 100 flights, and we started coming up with, as a computer scientist, really terrifying numbers, that there were 10 to the 13th, so one with 13 zeros after it, even for this really simple problem. And then we're looking at the original problem, and it's orders of magnitude larger than that. So this was the time when the scalability challenge really came into focus. We limited the problem somewhat initially by focusing just on the international sector, but even that was extremely challenging. And the core problem here was the very large number of defender strategies. So if we looked at the transition, the original armor problem had hundreds of actions for each of the players, and the air marshals is, we can't even list the numbers in a font that you can see. So when we tried to run our solvers that worked nicely for the original armor problem, you get up to tens of flights, and the system just crashes, runs out of memory, can't solve it. And we're talking about trying to get orders of magnitude larger. So an interesting problem for us computer scientists. I'm not going to go through all the clever techniques that we have come up with over the years to try to improve the scalability and to be able to solve real-world size problems. But there are a number of them. And in each of these categories, we have probably tens, if not more than that, papers that have been written by PhD students, doctoral theses that have been written about solving a lot of these problems. So we could certainly go into a lot more detail. Just to give one very high-level intuition for one of the ideas that was used in Armor, the core problem is all these combinations of schedules. So as you increase the number of air marshals, you have lots of different ways to assign them in combination with one another. That causes this is one of the few mathematical slides I have. This is actually a representation of an optimization problem. That becomes very intractable as you have all these combinations. But when you look at the problem itself, you start to notice a lot of repetition, and that it leads us to compact representations that eliminate a lot of that repetition. So we came up with ways of representing this problem in a much more efficient way, and that allowed us to, at least for this system, scale quite dramatically to larger and more complex cases. That wasn't the only trick we had to use. There was also some more advanced optimization techniques that had to be brought into bear. But eventually we were able to get positive results. So as computer scientists, we often show these kind of runtime plots showing how well we're able to do in terms of algorithms, and this is the kind of thing that we like to see. So the original Armor system, as you increase the number of targets, the runtime is just shooting up dramatically. Our more intelligent algorithmic designs let us scale up. We've got up to 20 targets here, and we're almost instantaneous. And when we started looking at the more realistic scale problems, we were still able to solve those within seconds, as opposed to hours of computation time, or not even be able to solve the problem at all. So the scalability issue is maybe not that much of interest to many of you. It's of great interest to the computer scientists, but this is one of those real-world challenges that just about every problem we've run into, you've got to do something to address scalability and be able to actually analyze the complex problems that arise in the real world. So the next thing that I want to talk about a little bit is the human behavior, the human element. So a lot of basic game models, the starting point for analysis has always been perfect rationality. So perfect rationality is easy to capture mathematically. There are only certain ways that somebody can be perfectly rational and maximizing their goals effectively. Humans don't always behave perfectly rationally. There's a number of reasons for this. When we talk about modeling games, we have to make a lot of assumptions to be able to write down an explicit model of the game. And some of these assumptions involve, for example, what are the utilities for an attacker for different outcomes, right? So how much does an attacker prefer one kind of outcome to another? Okay, so we have to try to say something about that. What does the attacker know about the defender's strategy? Okay, there's different assumptions we can make there as well. We can assume complete observability. We can assume that they don't know anything about the defender's strategy, or something in the middle. We can assume some sort of partial observability kind of model. But again, we're making assumptions to try to construct a model that we can analyze. We could also we have to make assumptions about what procedure an attacker is going to use to make a decision. And perfect, these rationality models where they're maximizing expected utility is one way that they can make a decision, but there may be other ways, particularly if there are human adversaries. It may be difficult to describe exactly how they might reason about the game and make a decision. And the reality is that even the best models that we can construct are going to be estimates of the real situation in interesting ways. So a lot of the research directions that have been pursued have tried to address various aspects of how we are approximating the real world. So one big picture research direction that we published a number of papers in is trying to improve and validate more accurate ways of modeling human behavior that go beyond just rational agents. I'll talk about just a couple of examples of that. Another big picture direction that we've been pushing in is trying to come up with ways of analyzing these models that are more robust and take into account the fact that the models are approximations and that there may be uncertainty about the model itself in different ways. So we want to build in some robustness into our analysis. And then the final direction, which is fairly new, Aranesh talked a little bit about learning in the final part of his presentation. We've also been doing some other work on making our models more adaptive and being able to take into account additional information, additional observations that we may have, and learning to improve our models over time. Okay? And that also has the effect of making us more robust and adaptable. So first, on the human behavior element, there's a whole branch of research called behavioral game theory. It's a subfield of game theory, which jumps off from the observation that when we take human beings and have them play games, had you play a very simple game in the early morning session, we do this to humans all the time in laboratory settings to try to see how humans actually make decisions in these kind of simple games. And then, so the first analysis is almost always, well, humans are not behaving according to a Nash equilibrium kind of prediction, right? They're deviating in all kinds of ways, and moreover, they're not even necessarily playing that predictably. It's not that everyone always plays a game the same way. There's a lot of variation in how humans play games. There are some predictable patterns, but certainly not easy to predict exactly how humans are going to play. So the agenda of behavioral game theory is to try to come up with better descriptive models for how humans actually play and then test them in these laboratory experiments and ultimately perhaps even in fielded studies of real-world interactions. So we draw on observations and techniques from psychology and experimental economics to try to motivate us to find more predictive models. And there are many different phenomena, different kinds of models that have been proposed and tested to varying degrees about how humans actually make decisions in the real world. So I've listed a few here: choice theory, prospect theory, anchoring biases. So anchoring bias is this notion that you tend to anchor on certain kinds of solutions, like uniform distribution may be a natural anchoring point, subjective utilities, and many more. So what we've been pursuing in the security games literature is behavioral experiments, trying to integrate some of these models from psychology and then testing them out in laboratory experiments designed to mimic these kinds of security decisions. Okay. So we're going to actually recruit human participants. We're going to get them to play games. We can recruit them from different sources. We often recruit from Mechanical Turk because it's fast, cheap, and relatively easy, although you can also recruit from populations of students, or if you have the resources, you can try to get pools of, say, security experts to try to play these games as well. The image that we have on the right here is an interface to one of the early experiments. This is an experiment that's actually designed to mimic the decision-making that's taking place in the armor application from the attacker's perspective. So there are 8 options representing the 8 different terminals at the airport. We present to our participant in the experiment some information about what their potential gains are if they choose one of these options, and also what their potential losses are if they choose an option which is being protected. We present to them information about the defender strategy. So recall that we are modeling attackers who have surveillance capabilities. So we actually present to them information about the strategy that's being played against them. So there's probabilities here that there's not going to be a guard in each of these options, or that there will be a guard. And then there's also information about what the guard's payoffs are. Okay, so these games are presented to the participants with instructions. There's some practice games that are played to make sure that they understand the game. And then we let them basically play the role of the attacker and see what they actually do. They are rewarded for success, so we pay them real money when they're successful in making good choices. And we can then see the patterns of behavior, and we can test different game theoretic solution algorithms, including these different behavioral models, against actual human decision makers. Okay. So there have been quite a number of these experiments conducted, not just in this game, but in games that reflect green security games, these kind of poaching scenarios, and others. We've also looked at a number of different kinds of behavioral models. I'll give you just one example of a behavioral model that we've looked at called a Quantal Response equilibrium. This actually comes from early work in choice theory, which basically showed that people do not always pick the very best alternative. They are not perfect maximizers, but they do tend to make choices that follow a distribution where higher valued choices are picked more often. So that's called a quantal response. So quantal response can be used in game theory by replacing a normal best response, where you choose the optimal response to whatever the opponent does, with a quantal response that basically adds a noise term, and there's a parameter within this quantal response that interpolates between purely random responses on one hand and a purely rational response on the other hand. So you can kind of smoothly vary the amount of rationality that you are assuming. So that's this lambda term. And when we integrate this into game models, now we can compute an optimal response against an attacker who's behaving according to some level of noise or irrationality in their response function. Okay. So that's one example. To give you an example of an experiment, so this is an experiment run using the kind of game interface that I showed you before, with 7 different payoff structures. So we can generate different kinds of payoff structures, different reward levels, and so forth. In this case, we used 5 different techniques, 5 different strategies with different including this quantal response and also a couple of other different behavioral models. So the participants played all the games, and in this case, they did not receive any feedback until all the games had finished. And we can measure what is the average defender expected utility. So basically, how well do these strategies do against the actual, the human participants in these games. So this is 4 of the payoff structures. You don't need to understand for now, what all these different bars mean. They're all different variations of behavioral game theory algorithms that we've tested to see which ones do best. So the important thing is that so that these yellow lines here represent the perfect rationality solution. We assume the attackers are perfectly rational, and we optimize against that. And several of the different behavioral solution concepts are able to improve against the human participants over the perfect rationality models. And in this case, the best response to the quantal response equilibrium that I mentioned on the previous slide does consistently better than all the perfect rationality models, and it is the best overall among the behavioral models that were included in this experiment. Okay. So this is ongoing work. This is a long-term research agenda to try to explore the advantages and how good these behavioral models can get. There's a lot of validation, a lot of experimentation. These experiments take quite a while to run because you actually have to go out and do an experiment with people and analyze the results. But it has been shown that we can do better than just assuming perfect rationality at targeting our responses against the kind of decision-making processes that humans use. I'll just mention that the current leading model, which at least the last I heard is doing the best among all the models, is a version of Quantal Response that also includes something called subjective utility. So there's some additional parameters where you can modify how you are assuming the participants perceive their utilities. Okay. So that is one direction that we've been pursuing with respect to human behavior. I now want to talk a little bit about some things that we're doing more generally about robustness to uncertainty, about other parameters of the model. So the idea here is that we want to be able to account for other kinds of uncertainty in our model itself. So one big example is payoff uncertainty. So when I showed you that matrix, I wrote down a number that said, if target 1 is attacked and it's not defended, the payoff for the attacker is -2. Okay? That's a very specific number. So it's likely that we have some information about the payoffs in the game, especially the defender's payoffs, maybe less reliable information about the attacker's payoffs. But for both of those cases, there's likely to be some amount of uncertainty about those values. There may also be uncertainty about the observations that we have. So in cases in these games where players are making observations about each other's strategies, there may be uncertainty about that. There's also decision-making uncertainty, which relates to the previous section where it's talking about human behavior. So humans may make decisions in lots of different ways. So we've looked at different ways of representing this kind of uncertainty, and I'm going to talk about a few of them that relate to payoff uncertainty, although these methods can also be used to capture different kinds of uncertainty about the game models. So one that we already encountered previously in the morning talk was we call a finite Bayesian game. So here we're modeling a small set of different types of attackers. So the idea is that we are not sure exactly what type of attacker we are facing, perhaps an attacker with a different kind of capability or a different motivation. But there's a small set of specific attackers that we might be facing. We can capture that in a finite Bayesian game. So we have a different utility function represented for each possible attacker we can be facing, and we can translate that into a larger game and solve it using an optimization model. Okay. So that doesn't change things too dramatically, except for making the game larger and harder to solve. Another way that we've looked at to represent uncertainty is what we call a distributional payoff representation. So this takes the approach that, so we may not know exactly what the payoffs are. So we want to be able to model a range of possible payoffs and actually the likelihood of different payoffs within that range. Okay. So before, for each target, we had just two numbers for each player. So one represented what is the payoff if it's a successful attack, and one represented the payoff if it's not a successful attack. So in these kinds of models, we actually have a probability distribution that can be an arbitrary probability distribution over possible payoffs for each of these two cases, right? So on the graph here, a higher number represents a payoff which is more likely. Okay, so this allows you to do things like saying, the payoff has maybe a Gaussian distribution centered around this particular value, and we have more or less uncertainty depending on the standard deviation. Although we don't restrict ourselves to Gaussians, we can allow arbitrary distributions over payoffs for these kinds of models. Okay, so now instead of having a point value, we have a more expressive distribution over possible values. These games are, in fact, very difficult to solve, but we've come up with a lot of algorithms that we can use to solve these games, to find good coverage strategies, taking into account this uncertainty about the actual payoffs in the game. And I'll show you one slide of results here. So This is the defender's expected payoff on the y-axis. We're varying here the amount of uncertainty about the payoff. So the variation between our payoffs and the ground truth payoffs. That's how to think about this. And we have a number of different solution techniques here. You don't need to know what all of them are. What I will show you is that these two bottom lines here are solutions that assume perfect information. So they basically take the ostrich approach, and despite the fact that you have uncertainty about the payoffs, you just take the mean of the distribution, for example, and assume that that is your payoff in the game. So you ignore the uncertainty that you have about the payoffs. And what we find is that those approaches are quite brittle, and it's okay if you don't have any uncertainty at all, but as soon as you start adding some noise into the model, the payoffs drop off quite quickly. These upper lines here, so the green one is an approximation that does sampling in only one dimension. The top lines are sampling and approximating both about the type, and they are approximating the optimization. And we find that these are able to be much more robust to this kind of uncertainty. As you add more uncertainty, your payoffs are naturally going to go down, right? So you can't optimize as well when you know less information. But they fall off much less dramatically, so if you have a little bit of noise, you can still do very, very well. And even as you add much more extreme levels of noise, you're still doing much better than if you simply ignored the fact that you had uncertainty. Okay? So the main point here is that uncertainty exists. We have it in our models, and our models do not perfectly capture the world, but we do have computational techniques for accounting for this kind of uncertainty in our models. We can solve those models, and we can have much more robust solutions than if we just ignored the uncertainty. So both of these are what we call Bayesian games, in that they have specific distributions that express the likelihood of different types of events. So these are great in certain ways because they are very general frameworks for modeling uncertainty. And we can get exact behavior predictions based on these models. But they do have some limitations. So they require this distributional information. So they require you to specify a whole distribution over the possible values. And that could be difficult to specify. So there's even more parameters that we need to get from our data or from our experts who are providing the values. And they can be wrong about what the distribution is. And as I mentioned, the models are extremely difficult to solve, so it's very hard to scale them up. We have to do a lot of approximation if we want to solve really large models. So another variation of a way to capture uncertainty that we've looked at is using intervals instead of distributions. So what this allows you to do is, instead of, again, specifying a single point value, we specify a range of values. And we say that the value could be somewhere within this range. Right? So for example, we could say that the attacker reward for attacking target 1 is somewhere between 1 and 3. Okay? So it gives you a larger range of possibilities. Now, as I said, there's less information here, so we don't know anything about the likelihood of different values within that range in this model. All we're saying is that the values fall within these two extreme points. So that leads us typically to do something like maximizing the worst case that we can have for any attacker value within this range. But it is distribution free. It allows us to analyze these games. It turns out that they are much easier to solve. So we can actually solve these in computer science terminology. It's in polynomial time. We can solve these kind of interval security games. In practice, we can scale up to millions of targets, whereas for the distributional games, it may be hundreds. Okay? So this may be the only option for representing uncertainty if you really have a massive game and you do want to capture uncertainty about payoffs in some way. And again, this is a single slide that shows the payoffs. So this bottom line, again, is the ostrich approach of ignoring uncertainty that we have. So just using a point value in the middle of the interval and saying, okay, we're going to solve this just using our normal game algorithms. We can see that that approach gets very low payoffs. The other approaches that do account for uncertainty, these are several different algorithms that we have that have different computational costs, but all of them do much, much better and are actually quite robust to adding uncertainty into our game model. Okay. So the next thing that I wanted to give you a flavor about is some of the work that we've been doing very recently using learning. Okay. So the starting point here is that in many games, we actually do have repeated interactions with an adversary. Okay. So our original game modeling, we were thinking mostly about terrorism and airport security and these kinds of incidents. And unfortunately, there we're in a fairly data-poor environment because we don't have that many incidents. We don't have long repeated interactions that we can observe. But there are many other types of security domains where we do have lots of data and we are repeatedly interacting with an adversary over time. And that leads us to a different kind of way of thinking about these game models where we have a repeated game, multiple interactions, and it allows us to learn about an opponent. It also allows them to learn about us, right? So this has led us to think about different kinds of game models where we're using machine learning kinds of techniques to update game models over time based on observed behaviors. Okay. And one of the issues that comes into play that I'm going to talk about is the need to explore, or also think about this as maintaining situational awareness in certain domains to be able to learn about an attacker's responses and perhaps learn about how the situation or attacker behavior may be changing over time. Okay. So I'm going to motivate this from the context of a simple border security kind of scenario. We've also been thinking about this recently in the context of network security, where again, there's lots and lots of data, lots of probing and attacks that are going on over time that we can attempt to learn from. Okay, so to investigate this issue, we came up with a very simplified abstract model that we think captures something interesting about how these defender and attacker interactions can evolve over time. So this is a resource allocation scenario based on the idea of there being a number of zones that you want to patrol, perhaps in a border region. In our green security games, it could be regions in a park or something. So we're going to model this just as having a fixed number of zones. And the key difference here is that we're going to model multiple rounds of interaction over time. So we're going to play this game repeatedly, and the players are going to observe what happened in the previous rounds and be able to update their strategies for future rounds. So there's going to be multiple attackers in this case. So there's going to be many attackers who are making decisions of which zone they are going to attempt to cross through. And the defender is going to patrol one zone, although we could generalize that and have multiple resources. But for simplicity, we're just going to assume that the defender picks one zone. Okay? And in each round, the defender then goes to this zone and apprehends the attackers who try to cross in that zone, or who select that action, and does not observe anything that happens outside of that. Okay? So there's an interesting trade-off here between going to places, like in the criminology example, where you know that there's a lot of activity, and learning more about what's happening in other places that you haven't observed activity. And this is especially relevant in dynamic situations where the patterns of activity may change over time, where the attackers may be learning about where we are placing resources and adapting and modifying to that policy over time. So interestingly, this kind of scenario maps very neatly in certain ways into a problem which has been studied in machine learning called a multi-armed bandit problem. So in a multi-armed bandit problem, the basic idea is that you have a bunch of slot machines, each of which you can pull the arm on one of these slot machines, and it is going to give you an unexpected payout. Okay? So this is motivated by a kind of casino example. I love the octopus pulling all the slot machine arms. I like presenting this slide just to show that picture. But the basic problem is you want to decide which arm you're going to pull in each round to maximize your overall payoff over the course of many rounds. At the beginning, you know nothing about what is the payoff in each of these slot machines. So the only information that you get is you pull the arm on a slot machine. In one round, you see what result it gave you. Okay? But they're not going to be consistent, right? There's going to be a distribution of payoffs that you get from each of these machines. So you have to pull the arm many times to get a good estimate of how good this machine is versus another machine. Okay? So the fundamental problem that this exposes is balancing what we call exploration and exploitation. Exploitation is I want to pull the arm that, based on the information I have so far, is going to give me the best payoff. Exploration is I may want to pull arms that haven't given me the best payoff in the past to learn more about what their payoff is, to see if maybe they actually have a higher payoff than what I've estimated based on my history so far. Okay? So there's a fundamental balance between learning more about the environment and exploiting the knowledge that you have. So if the attacker in our simple border scenario chooses zones with fixed probabilities, this is exactly a multi-armed bandit problem. In the more realistic scenario where the attacker can actually adapt and change behavior themselves, this turns into a different version of the problem that we call an adversarial multi-armed bandit problem, where we make assumptions that the attacker or the arms in this bandit problem may actually have their values adversarially changed over time. And there are learning algorithms that have been proposed. I won't go into the details, but the interesting thing is that we have algorithms like UCB and EXP3 that tell us how to balance our exploration and exploitation actions such that over time, as we have large numbers of interactions, we're going to converge to always playing the best strategy. Okay? And that is true even in the case where we have an adversary who is actively trying to minimize our payoffs, in the case of this EXP3 algorithm. And the way, just to give you a little bit of intuition how it works, is basically you always have some exploration that's going on for the arms that seem to have low values. And if you observe a change in one of those arms, you very quickly reevaluate how valuable that arm is, and you devote a lot more resources, a lot more arm pulls to quickly trying to learn what's going on, what has changed. And so you reweight very quickly to respond to changes in the underlying distributions. So we've done a number of experiments in simulation, exploring these kinds of learning algorithms in this basic border patrolling scenario. So these lines represent both the pure learning algorithms. So EXP3 in particular is this blue line here. But they also represent a number of other learning algorithms that are combined with some prior information from an equilibrium analysis. So basically we're taking an estimated game model, using that as a starting point, and then learning and updating that game model over time. And the interesting thing that we find from that is that we can get the advantages of very quickly, we don't have to have the sort of slow start of a learning algorithm. We can take advantage of the information that we know immediately, but then we also converge to a high value. And we've also done experiments where we've looked at things like introducing injecting changes, so the adversaries' payoffs or behavior change at different points. And these learning algorithms are quite robust and are able to detect that and quite quickly rebound to higher values. So the last topic on my agenda for this session is talking a little bit about evaluation. So you've seen a few slides throughout about evaluation, but I want to give you a little bit more of a big picture about some of the kinds of evaluations that have been done, especially of the deployed systems. And evaluating these systems is not easy. It is quite difficult to get access to the data. It can be difficult and expensive to perform experiments. But we've done a number of different kinds of evaluations to try to assess how well these systems are doing at optimizing limited security resources. So the core question is, so all these methods that we've presented that use this methodology of security games and modeling these scenarios using the tools of game theory, are they superior? Do they actually show advantages in comparison with the relevant baselines? And two relevant baselines here would be the human schedulers, the human experts who have often been doing these scheduling tasks prior to implementing these systems, or other benchmarks, so baseline simple randomization strategies or heuristic randomization strategies that are not fully optimized. And we've done a number of different types of evaluations. So the first step would be lab evaluation, so we can do evaluations against simulated adversaries. So you've already seen some examples of that. We can do lab evaluations against human subjects, as in the behavioral experiments. The next step would be doing field evaluations to experiment with the systems in the field and look at the patrol qualities, to look at the unpredictability, the coverage kind of properties that these patrols have in comparison to what was done before. So we can do comparisons with real schedules. We could do scheduling competitions where we can try different solutions against each other and look at the results. And then we can also have experts look at these schedules and try to assess which ones are better and for what reasons. And finally, the gold standard in some sense would be, seeing how the system works in the field. So we can try to see how well these systems do against mock attackers or red teams. We can also look at what actually happens when these systems are deployed, so we can look at what data we are able to collect and analyze about capture rates of actual adversaries. Now, the amount of data that we have is going to be very domain dependent, so I'll show you a couple of examples of that. So why does game theory perform better? So human schedulers, they have predictable patterns. I'll show you an example of that on a slide in a moment. But they also have a lot of effort, cognitive burden, a lot of time that goes into scheduling. So that is a downside compared to just being able to hit a button and let the computer do the scheduling. If we compare to simple random dice rolling techniques, uniform random kind of strategies, those repeatedly fail in deployments. So they're susceptible to things like sending officers to very sparsely populated terminals, and nobody wants to be protecting an empty room. You want to be where the action is and where the actual risks are. So we can also think about weighted random kinds of strategies, but what is the right kind of weighting? You can look at the different types of weightings, but they all are reliably inferior to the optimized weightings of the game theoretic models. So let me present a few slides. There have been many more experiments than these that have been done, but these are some examples of the different types of evaluations that have been done. So this is a simulation experiment with the IRA system for FAMs, where we compared two different types of weighted random strategies, as well as a uniform random weighting compared to the IRIS system. This is just different different sizes of schedules, and we are looking at the defender expected utility, and we found in this system using the actual payoff values that were entered into the system by the air marshals that the utilities for the IRA system were dramatically higher than the defender expected utilities. But that's just an experiment in simulation. This is a field evaluation that was done for of the schedule quality for the PROTECT system. So we haven't talked in detail about the PROTECT system. It's similar to IRIS and ARMOR. This was done for the Coast Guard, so this is helping to schedule and randomize patrols for the Coast Guard, first in Boston, and that's where this data comes from. And so they actually had thought really carefully about how to test the system before it was deployed. So they did pre and post analysis of what their patrolling schedules looked like before PROTECT was deployed based on what was being done by the human schedulers, and then after PROTECT was deployed. And this is across the 7 days of the week. So these are lines representing different targets that had different values. And the x-axis here is the count of the number of times that these targets were patrolled on different days. Okay? And the graph here, the thing to notice, two things. One is this dip on day 2, right? So for some reason, there's a lot less patrolling activity going on day 2. So if I'm an attacker, I'm definitely thinking about planning an attack for day 2 instead of any of the other days out of the week. And there's also a lot of crossing in these lines. There's a lot of inconsistency in some targets are being patrolled more on certain days and less on other days, and so forth. This is what the graph looks like. Same process, same data collection after PROTECT was deployed. So you can see we no longer have this dramatic weak point in the patrolling. So now it's evened out, so there's a much more consistent patrolling pattern across days. And also you can see that the lines are much more even across the days. And what that reflects is that the targets that have the higher risk values are being consistently patrolled more frequently, and there's no variations of that across the different days that could potentially be exploited. And when they calculated the expected utility for the defender, this resulted in a 350% increase in the expected utility, driven by the fact that, before PROTECT, a rational, intelligent attacker is going to exploit the weak points in these patrolling strategies. So another evaluation of the scheduling system, IRIS, was done by the Federal Air Marshals. So they actually did a version of this test internally, so we don't have the actual data to present because that is sensitive. But so they did exactly this test where they had their previous human scheduler schedule the flight patterns for the FAMs, and they compared that to the IRIS flight patterns. And over a 6-month time period of looking side by side at these schedules, they determined that the IRIS system was scheduling more effectively. And there's actually a GAO report that talks about that analysis that was done. This is another system, trusts, that we haven't talked about in great detail. So this is actually a system that was developed in coordination with the Los Angeles Sheriff's Department for optimizing patrolling on the metro system in Los Angeles. And one of the interesting things about that system is that we actually get a lot more data because they're doing things like checking for fare evasions, which happen much more frequently than terrorist attacks. So they're able to do some systematic tests. So this is one of the results from a test. This is an expert evaluation of comparing the game theory schedules to human-generated schedules on these trains, and they had some questionnaires that they had the experts evaluate these schedules and look at whether they made sense in different ways. And the game theory solutions were consistently evaluated as better than the human schedules. There have also been some field tests done against red teams or mock adversaries. Again, one of the examples of where this was done was the Protect system. So they did these sort of mock attacker teams who actually went out and were observing what was going on in the Port of Boston pre and post Protect. And their evaluation was that deterrence improved. There were also some interesting real-world indicators. So, so one of the chiefs there in Boston, so after Protect had been deployed, started getting questions about whether or not the Coast Guard had actually recently acquired more boats, and of course they hadn't. They were using the same number of boats, but because they were appearing at different times in different places than people were used to, the perception was that they were all over the place and they were in more places than they had actually been patrolling before. So another example of a field test against real adversaries, this is again with the trust system, where they did a controlled experiment. And they were evaluating the game theory solution versus a random patrolling on the Metro rail system. They did 21 days of patrolling. Identical conditions, so a true controlled experiment where we have system A and system B. We're trying to match them up under conditions that are as close as possible. And they also did a version of they're calling random plus human. So that is a randomized schedule, but that the humans are allowed to modify at will. So the humans can say, this action doesn't make sense. We'd like to go here instead. Okay? So it's injecting some randomness, but it's really human scheduling as well. And here's some of the data from that experiment. So this is measuring, and they were looking at things like fare evasion attempts on the network, as well as other kinds of violations. And this is the number of captures, the number of warnings, and the number of violations in an average 30-minute period, comparing the game theory optimized solution compared to the solution where there was a randomized schedule, but then the humans were allowed to modify that schedule in whatever way they wanted. And what we observe is that in all of these different categories, the game theory solution is actually resulting in better detection rates than the other schedules. There's also results and data that we can collect not from controlled experiments, but just by observing what happens. So that was the first kind of data that was collected at LAX. So they looked at the drug apprehensions, at different kinds of behaviors that they were detecting at the checkpoints before and after they deployed the armor system. And what they noted in the data, again, this is not a controlled experiment, but there was a pretty clear jump in the detections that they were getting after they deployed the armor system. Okay. And finally, again, in the category of expert evaluation, several of these systems have been deployed consistently over years at a number of these different agencies. They're not forced to keep deploying these systems. They use them because they're viewed as effective and useful additions to the security policies. And these are a number of different awards and commendations that the team has received over time for successfully deploying these applications. And there's a lot of appreciation, I think, on both sides for the successful partnerships that have been necessary to get these applications deployed. So that's all I have for now, but I'd be happy to take any questions.
Dr. Campbell, thank you very much.